So this is going to be about how to use summation notation to approximate area under a curve. So let's say we wanted to approximate the area underneath this very crude drawing of y equals x squared minus 9, but only between -3 and 3. That's where you can see that the graph kind of hits the x-axis right here. So if you want to do that, you could use summation, or maybe let's just say we're going to do, that's not what I wanted. Maybe let's just say we're going to do this part right here. So just from 0 to 3. And we're going to do that by using some rectangles. So let's say that we divide this up into 3 equal parts, and we pick this rectangle, and we pick this rectangle. It's kind of hard to draw these, and we pick this rectangle. Now this last rectangle doesn't have any heights because the right edge hits the graph on the x-axis. The right edge of this rectangle hits the graph somewhere up here, and the right edge of this one hits the graph somewhere up here. Now how do you know exactly where that is? Well, think about it. This is x equals 1, this is x equals 2, this is x equals 3. So if you wanted to find out these y values, or in other words the heights of these rectangles, you could use this function and find the rest of the ordered pair, and that would tell you your exact y values. Well, let's just say you wanted to use some summation, and we're going to be adding up all of these rectangles, which has an area of length times width. Each of these rectangles right here, this one doesn't have much height. They all have an area of length times width. This is what the formula you've always heard of. Let's use base times height for this example. Okay, and we are going to let x go from 1 to 3. The first one, the second one, and the third one. Now the base of all of these is 1. You can see that here. So this base is going to get exchanged for a 1. And these heights are given by whatever you plug in for x. See, if I want to know the height of this first one, I'll plug in a 1 for x. That's when x is 1. If I want to know the height of this middle one, I'll plug in a 2 for x. That's when x is 2. And you work your way all the way up till you get to when x is 3. And that'll tell you the height of this last one. So this is given by my function. So the area of this can be approximated by finding the area of these 3 rectangles, which is 1 times negative x squared plus 9, or just negative x squared plus 9, which has shortcuts. We remember, like the video before this. This is like a -1. So you just say -1. The formula for x squared is n times n plus 1 times 2n plus 1 all over 6. And the formula for a constant is your constant times your upper bound. And these 3 right here, you multiply these 2 together and then add that to 27. You're going to get the approximate value for the area under this curve. Which is 13 square units. And you can see that that's not an exact amount. That's actually not enough because there's red parts above each of these rectangles. So somebody might say, well, what if I made twice as many of these rectangles? What if I made a rectangle here, and then a rectangle there, and another rectangle here, and a rectangle here where this red crosshatch is, and then maybe another rectangle here, and another one there, and you would soon find out that even that's not good enough. And somebody else would say, well, maybe I could make more and more and more and more. And so you would say I need to make infinitely many of these rectangles, and what that would give you is, if you had infinitely many of these rectangles, that would make each rectangle razor thin, which would make the perfect contour up here on the top of every rectangle. It would hit this graph exactly once and come down all the way to your end. So what that would do for you is give you infinitely many rectangles, each of them infinitely thin, and that would give you the exact area of this shape. Now, you can't say the sum of the first rectangle all the way to the infinitely many rectangle. This has to be a number up here. So what we'll do is we'll say the first one to the last one, however many that is, and we'll let the number up here approach infinity. And we'll use a limit to do that. And so what that will give you is infinitely many rectangles, razor thin, and it will give you the actual area. And so the area will be given by the integral. This symbol right here is an integral symbol, and it tells you the exact area under this curve from A to B, or in this case from 0 to 3. So there's going to be videos later to show you how to do the area under a curve from A to B.